Unit 6 is all about systems of equations and inequalities. And in this video, we are going to start learning target 6A. So 6A is going to be about solving systems of linear equations. So by the end of this lesson, you will be able to solve a system of linear equations by graphing, and then without graphing, we will also be able to determine if a system of linear equations has one solution, infinitely many, or no solutions. So let's start with what a system of linear equations is. So a system of linear equations is two or more linear equations together. So it's when I look at a set or maybe three linear equations. In our unit, what we're going to look at is sets of linear equations. So we're going to look at two linear equations at a time. And how we solve that is we're looking for any ordered pair that makes all of the equations in the system true. So if I find an answer, it has to not only be true for one of the linear equations, but for both of the linear equations. There are actually three different methods for solving systems of linear equations. And in this video, we are going to focus on graphing. And in the next two later videos, we're going to look at how can we solve via substitution and elimination. So let's look at our first system here. So it says solve the following systems by graphing. So you guys will see here there's this kind of curly bracing on its side. That's just grouping the two equations together. So I know that I'm looking at this one whole system which has two equations. The first one is the y equals x plus 2. So this will be our first system. Y equals x plus 2 is our first equation in our system. And then the second equation we're looking at is also y equals 3x minus 2. So together, when I look at both of those systems, or both of those equations, that forms our system. Now, for us to solve this by graphing, we're looking for a coordinate pair that is true for both of these. So on a graph, we're looking to see where do these two lines intersect. Because if there's a point where those two lines intersect, then that point is true in both the y equals x plus 2 equation and the y equals 3x minus 2. In our last unit, we learned how to graph lines. So why don't you guys pause the video right now and list the slope and the y-intercept for this first line, y equals x plus 2. So our slope for this first line is positive 1, and our y-intercept, remember, we write as coordinate pairs, so that would be 0, 2. For us to graph this line, we know that we plot the y-intercept first. So I'm going to go up to 0, 2 and put a point there. I need 2 points to form a straight line, so I will use my slope to get my next point. This slope being equal to 1 means that it's the same thing as 1 over 1, which means I go up 1 and then to the right 1. So from my y-intercept, I'll go up 1 and to the right 1, and I'll put my second point. Now I could keep going, go up 1, right 1, and get another point and keep going all the way, but all I need is 2 points to form a straight line. So I'm going to go ahead and insert my straight line here. So if I was on paper, I would be using a ruler and I would be connecting these two together. Now you'll notice that I'm stretching this line across the entire coordinate plane. We're going to want to do that so that we can see where these two lines intersect. And if I draw just a kind of tiny little purple line, I might not find the place where the blue line is going to intersect the purple line. So we want to make sure that we're drawing this across our entire coordinate plane. For our second line, we're going to need our slope and our y-intercept as well. Why don't you guys pause the video and list the slope and the y-intercept for the equation y equals 3x minus 2. So our slope for our second equation is 3. Our y-intercept is going to be 0, negative 2. So to graph this, I'll go down to 0, negative 2, and I'll put a point. What 3 means is that I'm going to go up 1 and then to the right 3, since I can rewrite 3 as 3 over 1. So I'll go up 1, 2, 3, and then to the right 1. From here, this is enough to get a straight line, so I can go ahead and insert our straight line here. Again, I want to make sure that I keep extending this across the entire graph so that I can find the place where those two lines intersect. When I look at the graph now, it looks like they're intersecting right here. So that coordinate pair where we think they're intersecting is going to be at 2, positive 1, 2, 3, 4. So we're pretty sure these lines are intersecting at 2, 4, but we want to be absolutely sure. What if we accidentally made a mistake while we were graphing, or we counted incorrectly? So there's a way for us to actually check this. So I'm going to check and make sure that 2, 4 is actually a solution. And remember, for it to be a solution, it has to be true in both equations. So not only will I check 2, 4 in the first equation, I'll also have to check it in the second equation. And to check it, what we're looking for is we're going to sub in the values. So I will sub in 4 for y and 2 for x, and I get y equals 2 plus 2, and I'm asking myself, is that a true statement? And yes, it is. So that means that 2, 4 does work for the first equation. I have to do the same thing with the second equation. So we get y equals 3x minus 2, and I'm going to substitute in 4 for y and 2 for x, and I'm asking myself, is that true? So I'm putting this question mark over the equal sign so that I can remember that I'm looking to see if this is true. I don't know if it is true yet. If I simplify the right-hand side, we get 6 minus 2, and we're asking ourselves, does that equal 4? And indeed it does. So 2, 4 is our final answer then, because that's where our two lines did indeed intersect, and we check that by substituting it into both equations and making sure that the answer gave us a true statement. So one thing that you're going to keep hearing me say throughout not only this video, but all the rest of the videos in this unit, is that when we're solving a system of equations, our answer is going to be the coordinate pair that makes that true for both of those equations. So I wouldn't write my answer as x equals 2 and y equals 4. I want to write it as the coordinate pair 2, 4, because it's representing that point on the graph. Let's look at example 2. So in example 2, we have y equals 2x plus 4 as our first equation. And our second equation is going to be y equals x plus 2. Why don't you guys pause the video and graph this first equation, the y equals 2x plus 4. So to graph this line, we're going to need a slope and a y-intercept. Remember, m represents our slope, and in this case it's going to be 2, or we could write this as 2 over 1 to help us remember our rise over our run. And then our y-intercept is going to be 0, 4. Sorry, that got a little messy. That was a 0 there. Remember, y-intercepts we write as coordinate pairs. We'll plot the y-intercept first, so we're up here at 1, 2, 3, 4, and I'm going to put a dot. To use our slope, this means I go up 1 and to the right 1, since both numbers are positive, and I rise first before I run. So I'm going to go up 2 and to the right 1, and I notice I'm almost off the graph. So equivalently, I could actually go down 2 and to the left. Oh, I went over 1 too many. Oops. So up 2 and just to the right 1. I went over 1 too many there. So up 2 and to the right 1. But I'm still almost off my graph, so if you wanted to get a different point, I could actually go down 2 and to the left 1 instead. But all I need are 2 points to draw this straight line. So from here, I can go ahead and insert our straight line, and I just want to make sure I extend it throughout the entire graph because I'm looking to see where this line will intersect our next graph. Why don't you guys pause the video and graph y equals x plus 2 on your own first. Okay, to check this, I know that my slope here is 1 since we are in slope-intercept form on both of these, and our y-intercept is going to be at 0, 2. So I'll go up to 0, 2 and I'll put a point. From here, the slope being 1 means I go up 1 and then to the right 1. So up 1 and to the right 1, up 1 and to the right 1. What I'm noticing is that these lines are actually going away from each other up here. So it's not going to be possible for these lines to intersect in quadrant 1. So let's see if they intersect somewhere else. If I draw my straight line in there, This is why we want to make sure we extend it across the entire coordinate plane. And when we do, we notice that we're getting a point on the x-axis where it looks like they intersect. What coordinate pair would that be? So this coordinate pair would be -2, 0, since we went to the left 2 and we did not go up or down. Now that looks like where they intersect, but we're going to go ahead and check this just to make sure. And checking is going to be something that you're going to want to do on all of these problems so that you can make sure that your answer is actually correct. So let's check our first equation. So y equals 2x plus 4. I'm checking the point -2, 0. So I'll plug in 0 for y, and I'm asking myself, is that equal to 2 times -2 plus 4? And indeed it's going to be, because 2 times -2 is -4, and then -4 plus 4 does equal 0. So it worked in the first equation. Does that automatically mean that it's going to work as our final answer then if it works in the first equation? It's not enough to show that that actually works. I need my solution to be true in both of the equations. So I also need to check the second equation. So I'll sub in 0 for y. I get, is 0 equal to -2 plus 2? And indeed it is. So since -2, 0 worked in both equations, that is my final answer, and it is a solution to this equation. Now you might be wondering, could I get another answer that maybe I haven't seen on these graphs? Well, if we look at the graph in example 2, I have straight lines, which means as we move to the right of this purple line here is going to keep going up and up and up, and the blue line is also going up, but it's not increasing as fast, so they're only going to get further apart in quadrant 1, so there won't be another place. And likewise over here in quadrant 3, the blue line, is going out a little bit more to the left than the purple line is going a little bit further down, so these are actually getting further and further apart as well, so there is only one place where these can intersect. And if you think about it, if you take 2 pencils or if you take 2 pens, there's only one way for those 2 pens or those 2 pencils to intersect themselves, since they're both straight lines. Lines don't bend back on themselves, so for all of these, once we find one point where they intersect, then that would be the only point where they're going to intersect. Let's look at example 3. So example 3 says y equals -1/4 x plus 4 as our first equation. Why don't you guys pause the video and graph this first line, and we'll check it together. For our first equation, I know I need a slope, so that slope will be -1/4. That tells me that I'm going to go down, because I'll stick the negative sign with the 1, and then I'll go right 4. I also know that I have a y-intercept, and that y-intercept is 0, 4. And I got this information quickly because my line was in slope-intercept 4. So I'll start up here at 0, 4, and I'll put a dot. There's my y-intercept. Now from here, I'm going to go down 1 and to the right 4. 1, 2, 3, 4. And I have my second point. If you wanted to move where the negative sign was, you could also go up 1 and then to the left 4 would be another way to do this. But all I need is 2 points, so I'm going to go ahead and insert my straight line here, and I want to make sure, that it goes through all the points, there we go, and that it fills the entire graph. So I want to make sure it goes from one end of the graph paper to the other end. Let's look at our second line. Our second line says x plus 2y equals 6. Well, what form is x plus 2y equals 6 in? X plus 2y equals 6 is in what we call standard form. So remember, standard form was that form that honestly doesn't help us too much. It has the x and the y on one side and it equals a constant, but we can change a line from standard form to slope-intercept form by isolating the y variable. So to isolate the y, I'm going to subtract the x, so I get 2y equals negative x plus 6. Then to get y by itself, let's scroll down so I have enough space. I'm going to divide through by 2, but that means I have to divide everything through by 2. So the negative x and the 6 What I end up getting then is y equals negative 1 over 2 times x plus 3. And the reason we're getting that 1 over 2 is, remember, there is technically an invisible 1 here in front of the x with that negative sign. The reason I wrote it as a negative 1/2 is so that I can identify my slope. So my slope there is negative 1/2, which means I'll end up going down 1 and then to the right 2. My y-intercept I can also find quickly now, and that will be at 0, 3. So let's plot this line. So I go up to 0, 3, so 1, 2, 3, and I put a point. Ooh, those are already pretty close together, so hopefully they will intersect. I now go down 1 and to the right 2, and I put my other point. That's enough to draw my straight line, so I can use my ruler now and draw my straight line. But if I draw it that tiny, remember I have to keep extending it so I can see where these two intersect. So as I draw my line, making sure I actually go through the points, there we go, it keeps going, and it looks like the two of them intersect at this point up here. What coordinate pair is that point? So that point, let's count it, is going to be 1, 2, 3, negative 4, since I went 4 to the left, and then it went up 1, 2, 3, 4, 5. So that point there is going to be negative 4, 5. Now we could check this, it will work. I think it would be a great idea for you guys to pause the video right now and check to make sure that negative 4, 5 does indeed work and is a solution in both of those equations. Let's look at example 4. So in example 4, we have x plus y equals 4 and 2x minus y equals 2. So let's take this one line at a time. We'll start with the first one. X plus y equals 4. What form is that in? So this one is again in standard form. So how can I change from standard form to slope-intercept form? To change from standard form to slope-intercept form, I want to isolate the y variable. So to get y by itself, I'll subtract x, and I get y equals negative x plus 4. Why don't you guys finish graphing this first equation on your own first? So the other piece of information I'm going to need is that the slope is negative 1. So that technically I could write as negative 1 over 1, which means I go down 1 and then I go to the right 1, since the denominator there is positive. I also know that my y-intercept is going to be at 0, positive 4. That was a 0. There we go. So we can go ahead and plot 0, 4 first. So 1, 2, 3, 4. From here, I go down 1 and to the right 1, down 1 and to the right 1. But once I have 2 points, that's enough to use my ruler and draw myself a straight line. Making sure, of course, to extend this throughout the entire graph. So I've got to move it so that I end up off the graph paper. Now let's look at our second line. So we have 2x minus y equals 2. So this line is again in standard form, so we're going to need to solve for y to be able to get this in slope-intercept form. Why don't you guys pause the video and solve for y in our second equation? To solve for y, I'm going to subtract the 2x, so I have negative y still equals negative 2x plus 2. The last thing I have to do to get y by itself is divide through by that negative, and I end up with positive 2x minus 2. Now that we have that information, why don't you guys pause the video and graph that line. To graph this line, I need the slope, which is positive 2, or 2 over 1, will be helpful for rise over run. And then I also know that my y-intercept is going to be 0, negative 2. We start by plotting our y-intercept, so I'll go down to 0, negative 2. And then to use my slope, I go up 2 and to the right 1, up 2 to the right 1. But once I have 2 points, that is enough information to draw a straight line. And I want to make sure this line extends all the way on the graph. And what I'm noticing is I have a place where they ended up intersecting. So it looks like right here At that point, those two lines are intersecting, which means that coordinate pair will be a solution to this system. What coordinate pair is that? So that is the coordinate pair 2, 2, since I, from the origin, went right 2 and then up 2. Why don't you guys pause the video right now and check that 2, 2 works in both the first and the second equation. So I can do this kind of more as a mental check here. So if I plug in 2 in for x and 2 for y, I get 2 plus 2, which does equal 4. And in the second equation, I'll get 2 times 2, which is 4, minus 2, which gives me 2 as well. So yes, 2, 2 does work as a solution to this equation. So in these first 4 examples here, we saw how we could solve a system. And remember, a system is 2 or more equations together. For our unit, we're going to be looking at pairs of equations, so we'll always have 2 linear equations, and a solution to that system is where those 2 equations intersect. So on a graph, we can do that by graphing both of them and seeing where they intersect. Now, you might be wondering, we kind of talked about this, but so far we've only seen examples with one solution. Do you guys think that that's always the case? Is it only possible to intersect once? Could I intersect more than once? Could I not intersect at all, maybe? What do you guys think? So that's not the only case. Although if I'm going to intersect a finite amount of times, I will only intersect once. There are actually 2 other cases. So we've been dealing with this first case, which we call the one solution case. That's when the lines do intersect. So in our graph here, I have a blue line that has a positive slope and a green line that has a negative slope, and they are intersecting once. So I'm getting one solution there, and that's where those 2 lines intersect. That happens ultimately because these 2 lines have different slopes. So we know from our last unit that if lines have different slopes, that they will end up intersecting. If lines have the same slope, something else is going to happen, and that's what our other 2 cases will talk about. So we will get one solution anytime the lines have different slopes. And we can call this one solution because that's how many solutions we get, but a little bit more fancier of a word is that we would say that this solution is consistent and independent. The second case we have here is what we call infinitely many solutions. So we talked about earlier that if you were to take 2 pencils or 2 pens that you have in front of you, they're each representing straight lines. If they intersect once, there's no way for them to bend back on themselves to intersect maybe a second or a third time. The only way for them to intersect more than once is if they're actually the exact same line. And here I have 2 lines, you can't even see the blue one because the green line is completely on top of the blue line. So when I have lines that are the same, that happens if I have, the same slope and the same y-intercept. And when that happens, I actually have an infinite amount of solutions because they intersect everywhere. So each one of these points they're intersecting on, and I can't even draw all the points because there's infinitely many of them. So in this case, this is what we call infinitely many solutions, since the lines are ultimately the same line. A little bit more fancier of a word is we would call this consistent because there's still a solution. So both one solution and infinitely many solutions are called consistent because that means we have a solution. But this is called consistent and dependent because ultimately they depend on one another because they are the exact same line. Versus in one solution, they're called consistent and independent because they're 2 different lines and they have nothing to do with each other since they have different slopes. Our last case down here is going to be our no solutions case. So no solutions, we saw in our last unit that 2 lines might never intersect if those lines are parallel. So parallel lines, if I have a system of 2 lines that are parallel, then those would produce no solutions then. And that again happens when we have the same slope and different y-intercepts. So our no solutions happens when they're parallel because the lines over here, they never intersect, which means, intersect, which means I then have no solution. So remember, parallel lines have the same slope, that's going to be key, but they have different y-intercepts. So that's what makes infinitely many and no solutions different. So in infinitely many, we have the same slope and the same y-intercept, but in no solutions, we have the same slope but different y-intercepts. And we would call this inconsistent because there is no solution. So those are our three options. If I have a system of two linear equations, so two straight lines, they either intersect once, they either don't intersect at all, which would be our no solution case down at the bottom, or they're actually the same line, and in that case they intersect an infinite amount of times because I have one line on top of the other line. We're going to do some examples with how to determine this. So our next set says, without graphing, determine if the system has one solution, infinitely many, or no solutions. So if I can't graph these, I have to think about what features do the equations tell me. And what all of these come down to has to do with the slope and the y-intercept. If I have different slopes, then I automatically get one solution. If I have the same slope, then I could either have infinitely many or I could have no solutions. So if we have a pair of lines that have the same slope, I then have to look at the y-intercepts. If I have the same slope and the same y-intercept, I'll have infinitely many solutions. And if I have the same slope and different y-intercepts, then I have parallel lines, so I will have no solutions. So what we're going to do in each of these sets of examples is compare their slopes, and if necessary, compare their y-intercepts. So let's look at our first, our fifth example, but our first of this type. I have the system y equals 4x minus 1 and negative 4x plus y equals 2. The first equation is in slope-intercept form, so I could identify the slope and the y-intercept quickly, but the second equation I need to rewrite in slope-intercept form. Why don't you guys pause the video and write the second equation in slope-intercept form on your own first. To write the second equation in slope-intercept form, I need to get y by itself, so I'm going to add 4x to the other side, and I get 4x plus 2 equals our y value. Now from here, our job is to compute the slopes. What's the slope of the first line going to be? So the first line is going to have a slope that's going to be equal to 4. And what's the slope of the second line going to be? That slope is also going to be equal to 4. Well, since 4 is equal to 4, then in this case, I have these same slopes. So if I have these same slopes, I now have two options. I either have the exact same line or I have parallel lines. To figure that out, we have to look at the y-intercepts. So when I look at the y-intercepts, what's the y-intercept in the first equation? Our y-intercept in the first equation is going to be 0, negative 1. What's our y-intercept in the second equation? In our second equation, the y-intercept is going to be 0, 2. So in this case, I have different y-intercepts. Oops. So I have the same slope, but I have different y-intercepts, which tells me that I have then parallel lines. So these are lines that are never going to intersect. So will I have one solution, infinitely many, or no solutions? I will end up then getting no solutions for this system, since the lines are parallel. And no solutions, that is going to be our final answer for example 5. Let's look at example 6. We have negative 10x plus y equals 1. And y equals 4x plus 2. So in our first equation, I need to rewrite this in slope-intercept form. Why don't you guys pause the video and rewrite that equation in slope-intercept form. To rewrite this in slope-intercept form, I need to isolate y, so I'm going to add 10x to the other side, and I get y equals 10x plus 1. My second equation is already in slope-intercept form, so why don't I compute the slopes of both of these? What's the slope in the first line going to be equal to? That slope's going to be equal to 10. What's the slope in the second line going to be equal to? That slope's going to be equal to 4. So in this case, I have different slopes, since 10 and 4 are not equal to each other. So if I have different slopes, what does that automatically tell me then? Well, I have one solution, infinitely many, or no solutions. I will end up getting one solution. Because I have different slopes, it means they will intersect, and that they can only intersect once then. So I end up with one solution. Sorry, I don't know why this is delaying so much as I write it out. But since I have different slopes, I end up getting lines that intersect only once, so my final answer then will be one solution. Let's look at our last example. So our last example, we have y equals negative 3x plus 5 and 6x plus 2y equals 10. So in this second equation, we have to write it in slope-intercept form. So why don't you guys pause the video and write that in slope-intercept form. To do this and get it to slope-intercept form, I have to isolate y. So I'm going to start by subtracting the 6x over. Oops, plus 10. That was an x there. Now in this one, I do have to do one more additional step and divide through by 2. But remember, I have to divide everything through by 2. So the negative 6x and the 10. So I end up with y equals negative 3x plus 5. So my first line was already in slope-intercept form, and that's y equals negative 3x plus 5. My second line, now that it's in slope-intercept form, is the exact same thing. It's y equals negative 3x plus 5. So I have these same lines then. What will that tell me? Well, I have one solution, infinitely many, or no solutions. If I have the same line, it means the lines are lying on top of each other, so I get infinitely many solutions. Oops. There. Sorry, it's delaying. So because I have both the same slope and the same y-intercept, I have the same line, which means I end up having lines that, if I were to graph them, would be graphed on top of each other. So I end up intersecting an infinite amount of times. So I end up with infinitely many solutions then. So in this video, we saw what a system is. So a system, remember, is a pair or 3 or maybe even 4 or more equations together. We're going to look at only pairs of linear equations. We have talked about that there are 3 different ways to solve. Graphing, which we learned about in this video, and in the next 2 videos, you'll learn about the substitution method and the elimination method. And then we also looked at how the 3 different cases are, where if I have a system of 2 equations, they can either linear equations, they can either intersect once and I'd get one solution, they can intersect an infinite amount of times if they're the same line, and if they're parallel lines, they won't intersect at all, so that I get no solution. The key here is that we have to first put the lines in slope-intercept form, and we would want to show that work. We can then compute their slopes. If they have different slopes, we automatically get one solution. If they have the same slope, we then go and compare their y-intercepts. And if it's the same slope and the same y-intercept, we get infinitely many, since they're the same line. And if we have the same slope and different y-intercepts, then those lines are parallel, and we would end up with no solutions then. I do want to keep reemphasizing, though, the work of rewriting these in slope-intercept form, you do need to show on a learning check or on a final.